Algorithmic and high-frequency trading has gained great prominence in recent decades, with over 60% of worldwide trading now conducted automatically, a trend that will only continue to accelerate in the coming years. To this end, our research question was the following: how can market data be leveraged to develop a successful automatic trading strategy? A range of machine learning approaches to this problem have been documented, encompassing both direct price prediction, for example through regression or deep learning, as well as reinforcement learning strategies. We mainly focused on the latter of these approaches in our investigation. Now, a brief overview of the trading environment. We considered a market for a single asset, in our case this was Amazon stock, and at each time step we could take one of three actions: buying, holding, or selling, and each buy or sell action incurred a transaction cost proportional to the trade value. This deterred excessive trading and forced our algorithm to carefully evaluate trading opportunities. For our data sources, we used synthetic data capturing basic patterns for learning, in addition to 2 years of minute-by-minute data for Amazon stock. The train validation test split of the data is shown below.
We have implemented a deep reinforcement learning agent to tackle this problem. Our agent uses a deep Q network to map states directly into actions with the use of a neural network. Let's have a look at what information the agent uses. The blue window here indicates the market prices that the agent has access to at each step in training, with the top right dot here representing the current stock price. As previously mentioned, trading incurs a transaction cost, so we also want our agent to be aware of its last decision. Let's say our agent decides to buy. If the price goes up, it will be given a positive reward, and if the price goes down, it'll be given a negative reward. These rewards are used to update the network's parameters so it can make more profitable decisions in future. Feel free to pause here if you'd like to look more at the network architecture.
To determine the best set of hyperparameters, we use a service called Weights and Biases to help us streamline the process and visualize the results. We decided to tune the following hyperparameters such as learning rate, n-ticks, and batch size. To better visualize results, we also used the following heat map, where the best performing model is denoted by the yellow square.
The model is set to have an initial balance of $10,000, and it is evaluated on its portfolio values and actions taken throughout the trading period. Firstly, we implemented baselines. Notice that buying at the start gives portfolio values that are consistent with the prices, while selling at the start gives portfolio values that are inverted. The performance of these baselines are highly dependent on stock prices. Next, we evaluate the model on synthetic data. It performed well on the simulated sinusoidal data, where it took advantage of the low price to buy and sells when the stock price is high to earn profits. Finally, we evaluate the model on real data, where it sees 20 ticks of prices at a time. It bought at the start and around time step 50,000. It utilizes the change in prices and made decisions on trading actions, gaining around $1,400 in profit at the end.
After testing extensively on the validation data, we decided that it's difficult to make consistent profit. It could be due to noises in the environment caused by human trading activities. It could also be due to randomization in training data and within the model itself. In the future, we can investigate with different attributes in the dataset, such as high, low, and volume. We could also try to incorporate external datasets, such as stock news, so that we can analyze the polarity of the news.